to my lecture today. Of course, today we basically going to continue from regression diagnostics that we started on Monday. Of course, this week is about regression diagnostics, and of course, you know the significance of doing this. The significance of doing this is just that every statistical model has assumption, and before you can trust your model, of course, we actually need to investigate whether assumption hold or not. If assumption is violated, even though a particular matrix of evaluation is telling you that the model is performing well, then you cannot trust that. Okay, I'm actually going to refer to that as an accidental discharge of nature. It's not something that can actually be consistent. Okay, so in the outline today, there have been a kind of, maybe I'm going to say misunderstanding among the stakeholders between, they don't really know distinction between residual and error. Today, I'm actually going to make clarification on that. Then I'm also going to discuss the concept of art matrix, the significance of art matrix in regression world. Then I'm going to give further regression diagnostic hard codes. Okay, and because we are in election season in the United States, I'm probably going to be using an example from the election cycle to explain what I'm going to be, talking about today. Okay, before I go into this, let me say last night in the United States, there was a midterm election. And of course, I'm basically going to say the two parties actually won last night, and statistics also win last night. Research in general, we actually win last night. Everybody wins last night. And I'm actually going to say why. Before the election proper, there have been, poll conducted using statistical procedure. And of course, they really identify what was important in the mind of those who voted. Among what was important was inflation, the gas price, the reproductive rights, among others. So do you know that what was important, what the voters actually said was important, actually carried the day last night? And in this class, you can actually investigate using, for those of you who want to change your topic or who want to or do a private research on politics, like you can try to look at what was the connection between immigration, reproductive rights, maybe the right to abortion, inflation, the gas price, on securing electoral victory. Look at the electoral victory. Let your response be continuous. Talk about percentage of votes received by a particular candidate. Because if you want to base it on whether a particular candidate wins or not, linear regression is not going to work, no matter how you try, because the nature of the response variable is not continuous. Then a different type of regression that we haven't done in this class is going to be appropriate, that I call logistical regression. That's a very fine topic to work on, where you look at the effects of those periods on securing the electoral victory. Now, let me tell you this. If I want to look at the effects of inflation, gas price, reproductive right, threat to democracy, and some other predator on the percentage of votes received by candidates, I'm actually going to start with mean function that I'm showing you now. You know, the mean function is basically going to be a functions of those predator, and with the variance function that you need to specify to be a constant variance across board, where you're basically going to say the variation within the response, which is the percentage of votes received by candidates, when you go from one level of predator to the other will remain constant. That is our assumption, almost scarcity. Now, take a look at that 9.1. That is the mean function that we actually need to state. Now, after stating this, the next thing we actually want to do is, in the mean function, I need to estimate the parameters of, which I call the regression coefficient. Why do you need that? You need the estimate of regression coefficient because that's going to tell you the contribution of each of those predators to the response. And because of that, you're basically going to use, in matrix form, you're actually going to use this guy here. And with that, you'll be able to get the intercept, this depending on the numbers of predators you have. Of course, you know how to do that now, using the LM and stuff like that. Okay, now after doing that, you may want to make a prediction. It is not only explanation. It's not only, what is the contribution of this? For instance, you may want to make a prediction if a particular candidate, actually believe in reproductive rights or not, or is actually center his manifesto on bringing inflation down or not, or stuff like that. Can we have a way to predict the percentage of votes it's going to receive? Because of that, the Y cap equal to X beta cap will come into play. This guy here. You see the Y cap now, that's a prediction, right? So the Y cap equal X beta cap. When you take a look at this guy here, is the one that you have estimated, the regression coefficient. You now actually, this is like having a model now, a fitted model, right? A fitted model, okay? Now, when you have this as a fitted model, don't forget, if I plug in this guy to replace that here, I'm actually going to have this guy, right? Okay, now when you have this guy, here now, right? Okay, the one that has to do with X is the whole of this guy. I can rewrite this equal H, Y. That guy is art matrix. What does art matrix help us to do? It helps us to translate the observed into what? Into predicted. I'm going to say that again. Art matrix help us to actually translate, the observed into predicted. Don't forget, when you are working with data, you're basically going to have observed response. Like now, I'm asking you, if somebody is interested, you can go and collect the election data. Okay, you already know the percentage received by those candidates and what they believe in, right? It means you have the observed, right? From that, you can actually have the predicted within your data set. Okay, so take a look at that. What enables you to do that is because of the Hart matrix. But let me tell you this. So that's what you have here, which we call, so the Hart matrix is defined as that. But I wanted to focus on this. The Hart matrix only depends on the predator alone. Look at that. There's nothing like Y, right? Okay. But you know what? There is a mathematical property that this art matrix has to follow or has to attain before we can successfully, before it can successfully translate the observed into predicted. And number one, I think I mentioned that in this class, because this is a square matrix, n by n. It's a square matrix, okay? There are two conditions. There are two properties that need to be, satisfied before the art matrix can do the job of translating the observed response into predicted response. Number one, it has to be, a symmetric matrix. Okay? I'm talking about the properties now, okay, of art matrix. Okay? Number one, symmetric. What if examiner asks you, this is a theoretical question, investigate the symmetrical property of art matrix. And number two, idempotent. Okay? Now, by symmetric, okay, the transpose of that has to be equal to the original matrix. By idempotent, when I multiply that by that, it should also give me that, which I'm going to demonstrate to you now. You remember on Monday I promised today was going to be theoretical, right? Okay. Now, if I want to investigate the first one, please, I need you to pay attention. Math is easy, okay? It's not difficult at all. What I just need from you is focus the board. Now, what is our age? Okay, our age, the art matrix is basically this, S prime X, inverse S transpose. Take a look at that. Now we want to investigate that it is symmetric now. Okay, we need to find the transpose of this guy. So when I want to find the transpose of this guy now, I'm still going to write this, right? I'm still going to write this and I'm going to say the whole thing, transpose. If you don't understand, please ask me a question. Okay, I want to find the transpose of that. I basically want to see whether after finding the transpose of this, I'm actually going to get that. If I have that, that's symmetric, right? Okay. Now, this is what I'm going to do if I want to find the transpose. I will quickly need to go into mathematics. I'm actually going to group this guy into two. Okay, I'm actually need to recall, if I have AB transpose is equal to B transpose A transpose. You need to first recall that from mathematics. The transpose of the products is basically, they're going to change their position, right? We're going to have B transpose, A transpose. You got what I mean, right? Okay, now, you know what I want to do now? I want to call this guy A. I want to call this guy B. So let me say this guy A and this guy B, right? That's what I want you to do now, right? Okay, now, when you take a look at that, if I now want to rewrite that now where I have X, S transpose, this S transpose, okay? Now, I've called this guy A, I've called this by B. Now, if I want to write, I'm actually going to write this transpose, then X, S transpose X, then transpose. Take a look at that. This is what happened now. Okay? I call the whole of this guy A, right? I call this guy B. Okay? Now, when I do that, what I'm actually going to do now, I will write it this way. And the moment I have it this way, the transpose of the transpose is going to be that. Now, on this again, I'm going to call X A. I'm going to call this guy B. I'm going to apply that law again. Okay? When I apply that law again, this is already an inverse. Transpose does not work on inverse. Even though they're going to change their position, you're basically going to see, give me 1 second. So here now, so this guy is going to change. I have this guy, okay? Then I'm going to say transpose and transpose. Look at that. So this guy going to be x. The transpose of an inverse is basically going to be an inverse, and I'm actually having that. This is a transpose. Let us now compare this guy with this guy. Are they the same or not? Because they are the same, then it is symmetric. Any question on what I just did now? Mass is easy, right? Mass is so easy. Now, you can see I just demonstrate that. It is symmetric. Now, the next thing we want to do is, to show that it is idempotent. Okay? If I want to show that it's idempotent, I'm actually need to multiply that. Okay? So, I have this multiplied by this. So, what is my h? My h is actually this guy. Okay, x transpose, okay, multiply by this guy, okay, this, right? Okay, now take a look at this guy, okay, now and this guy, okay, you recall that A transpose A is basically going to be identity, right? When you take a look at that, I'm actually going to have identity for this, okay? Then I'm going to have x prime, x inverse x prime. And identity, is more or less like having this guy. So what do I have now? That also gives h. So which means it's an idempotent. Now that is what qualify Hart matrix to do the beautiful job of converting the observed value into predicted value. So these are the two properties, that actually need to be satisfied with. And let me tell you this. I'm not gonna do this. The implication of that, you can also show that I minus h is symmetric. And you can also show that I minus h is idempotent. You can try that. What if I give you this in exam? Okay, this identity matrix minus that. The symmetric with me when I use this to multiply itself, where h is that, it's going to give itself. The transpose of this is going to give the original one. And for idempotent, if I use this guy to multiply itself, it's basically going to give itself. Okay? I wanted to take note of that. Okay. Now, with that, because if I don't have a Hart matrix, we may not be able to get the predicted value. If we don't get the predicted value, then there is no way to obtain the error. Why do we need to obtain the error? Because in any statistical model, for us to rely on any statistical model, we want to minimize error. And if you don't have a way to compute that, there's no way you'll be able to minimize that. Okay? And take a look at this now. The error now is a difference between this and that. Now, let me now tell you this. When I'm talking about the error and the residual, I'm going to tell you the difference between them now. When I say error, I mean E without a cap. When I say residual, I mean E with a cap. Now the question now is, what is the difference between E without a cap and E with a cap? The E without a cap that we call error, okay, is a difference between the observed value and a true value. The E without a cap that we call error is the difference between observed value, okay, and a true value. That is the E. Okay, but the E cap, the difference between the observed value and the predicted value. There's a difference between a true value and a predicted value. I want you to take note of that. We call this guy residual. We call this guy error. Okay? And let me tell you this. In statistical analysis, this true value here is what we call population mean. And this predicted value here is more or less like a sample mean. Don't forget, we are working with a sample, right? We don't work with the entire population. Now, I want you to take a look at this now. Here, I'm talking about residual. Residual is different between the observed and the predicted. You see that? Y cap, right? Now, Y cap is X beta cap. You know that, right? Now, when I plug in beta cap into that, I'm automatically going to have this. You see that? It means if I want to estimate the error, okay, I actually need to translate the observed into that. And how can I translate observed into that? Then I need I minus at matrix. And the only condition under which this is going to do a good job is when I minus H is symmetric and is idempotent. Okay, the symmetric is just that I minus H transpose must be equal to I minus H. Idempotent in the sense that I minus H multiplied by I minus H must be equal to I minus H. That's what we mean. Now, take a look at that now. Any question on this? Without identity minus the hat matrix, there is no way we will be able to do what? We'll be able to translate the observed into the residual. Okay, I wanted to take note of that. Now, okay, go ahead.
It's like a real example of why you would want to do this. Like I understand like what we're trying to do here of like translating the predicted to the response to predicted values, but why would you want to do that?
Yeah, why we want to do that is more or less like I was talking about, predicting the percentage of votes received. If you take a look at this guy now, is basically the difference between, the actual value of the response in your data and the predicted. Okay? And that predicted, the difference between that now is that residual. And if this residual is very small, you know what happened? It means what your model predicts is very close to reality. Now, if I understand your question very well, why do I actually need this? These are stuff that happen behind the scene. When you were using your R, you don't know that a lot of stuff, that validate, like a theoretical provision that validates what you are doing is what I'm trying to explain now. All those things were possible because of the fact that this particular provision has already been mathematically proved and statistically observed. That is the reason. So this is what happened behind the scene. Without all this, you may not be able to do what you are doing with R. That's a good question. Okay, now, I'm no longer at residual now. I'm back at error. What did I talk about? What is the error? The difference between the observed and the true value. This is the observed, right? The true value, I told you, is always a population mean. Then for regression now, it's going to be the expected value of y given s. Look at that. Expected value of y given s. And expected value of y given s is going to be this. You can see this doesn't have a cap. The moment a beta has a cap, then you are talking about predicted. Do you get that? Don't forget, there's a difference between beta and beta cap. This beta here is a true population, coefficient. Do you know how you're going to get access to this guy? When you study the entire population, we don't have access to that. Well, let's take sample, and when the central limit theorem applies, okay, when you're working with large sample, Okay, we believe that the mean of this is basically going to be this. That's what we call bias. You get what I mean, right? Okay, now, this is the error now. Take a look at that. Okay, I just wanted to see the mathematical difference between them. Now, we go to back at residual. You know the other time, when we were specifying the function, we were specifying this function, okay? If you take a look at this is for population mean. This is more or less like the variance of y given s. That's a constant. But you know what? If I want to look at that in terms of residual, look at this. This is a residual now. Expected value of residual given the predator equal to 0 under assumption. But you know what? How do I get this? Don't forget, the variance of y given s should be sigma square, right? But the variance of error cap given s is going to be this guy. How? We're going to see now. Let's go back to let's come back here. Okay, I want us to come back here. I'm going to write something up now, and you're basically going to see what I'm talking about. Now, we have said residual is what? I minus h, y. Right? What is the expected value of this? It's going to be I minus h, expected value of y. Right? What is the expected value of y? When I say expected value of y, is the same thing as expected value of y given x. Don't forget, y depends on x. Right? Okay, so I minus h, expected value of, that would be x beta. Right? And in the end, let's make this, I multiply by that, this, minus this, h, x, beta, right? Okay, now, take a look at this now. If you make an attempt, probably you write x transpose x inverse. You know, in the end, without working that out, this guy is still going to be equal to 0. But if I want to come back and do the variance of this, don't forget, this is a constant. Okay? If I want to do the variance of that, I'm actually going to have this guy, the variance of y, don't forget squared. And because this guy is idempotent, I'm still going to have this guy because I minus h times I minus h is idempotent. It's going to be that. What is the variance of y? That is sigma squared. Look at that. That was what gave us this. Look at that. That was what gave us this. But without idempotent, we will not be able to get it. Look at that. Okay. Which means Hart matrix is very, very important. You know what? This material is what we're going to do today and what we're going to do on Friday. Okay? So I just want to prepare your mind. So that is now we can now have, how do we now have a relationship? Can we have a relationship between residual and error? Yes. You know the error cap equal to this, right? Then let us bring in y. What is y? This is y. You know, when I talk about y, okay, when you are specifying your original y, is a function of a deterministic part and the random part. I think you remember that, right? Okay, now y, this is equal to this guy now. Okay, and if I have this guy now, when multiply out, you're basically going to have this guy here. And it means if I want to translate the error, don't forget, the error is unobserved. You didn't observe it. In the case of what could make, what could determine the percentage of votes by a particular political candidate, I want to believe it is not all the factors that will be included in the model, right? Those predators that we did not include, they are unobserved. Why is it that we didn't include them? We didn't include them because we believe their effect is negligible. That's why we didn't include it. Now, let me now tell you this. This is unobserved. But you know what? I need the estimate of unobserved to be able to conduct inference in statistics. Without that, then there's no way we can rely on whatever we're doing and we cannot conduct any meaningful inference. We now believe now the relationship between residual and the error is this, which means I minus art matrix is the one that helps us to what? To translate the unobserved into estimated error, which we call residual. In a way, what do you think we're doing? We are in a way estimating the effect of predator that is not included in our model. Even though they are unobserved, we're estimating that. That's exactly what we're doing. Like I said, this is a lot of stuff behind the scene. Okay? A lot of stuff behind the scene. Now, the next thing I want to talk about is what we call the unusual observations that we call the outlier and high leverage point. Of course, the other time I told you when you are trying to set up a, specify a statistical model, we need to investigate some assumptions. And in addition to that, you also need to investigate unusual observation, outlier, and high leverage point. Of course, the outlier is when you have an extreme value in the response, and the high leverage point when you have an extreme value in the predator, and there's possibility they may be influential or not. And we have a way. Now I'm going to show you the mathematical way now. Now take a look at this guy here. HII. If you take a look at this guy, if I know the sample size, of course you have done this in class, sum of square deviation around the predator, and of course the square of that, you're actually going to have this at the HII. Now, we use this value of HII to decide on whether a particular extreme data point is influential or not. How? I wanted to take a look at this. I want to detect an outlier now. We can use residual. Observation with a large residual may be an outlier. What is residual? The difference between what you predict and what you observe. The large value of residual is a signal. It's like a red flag. Another measure is when we standardize residual because people believe that using the idea of residual may not be enough. Why can't we standardize that? If we now want to standardize that, we can make use of that leverage point HII with the residual itself and the standard, the sigma, which is the standard error, the residual standard error that you have in the regression output. You're basically going to have RI. This RI is what we call a standardized residual. That's an improvement on residual, okay, where the HII is defined as that. If you take a look at the HII, only focusing on what? On the predator. Look at that. You see the HII, right? And when you now take a look at the ROI now, okay, the ROI also put into consideration the response, because for you to get the ECAP, the residual, of course, you're going to be using the difference between the response and the predator, and the standard residual is another way to dictate an outlier. Well, you know what? we now have a range. Like, oh, if you calculate the standardized residual and you have a values that fall outside -2 and 2, then it's an outlier. Okay? I want you to take a look at that. And let me tell you this. That is the idea behind the residual plot that you always see. The residual plot is you know what they do in residual plots? In the residual plot, we are actually plotting residual against the fitted values. We don't expect any relationship between the residual and the fitted value because there's a relationship between residual and the fitted values. Then we're just trying to say our fitted values is just depending on residual, and we don't want that. You know the meaning of that? It means what determines the percentage of vote received by a particular political candidate is not even. I mean, what determines that is a predator that we don't even focus on in this model. It doesn't make sense. Don't forget, the predator we don't focus on in the model. Why is it that we don't focus on those predators? Because we have reviewed literature and we realize that their effect is very small. But let me tell you something. We could make a mistake. Don't you know that? There's possibility when an important variable is missing in a model, it could affect the model. But we're working on the fact that we believe that nothing important is missing out. So, and that was why we said if a residual plot should have a pattern, okay, then we don't have a straight line. It shouldn't have a pattern. Okay? So if it doesn't have a pattern, then there's going to be a straight line. Not having a pattern means there's no relationship between what I predict and the predator that I don't focus on in my model. That's what I mean. Okay? So, right now, I'm digging down, trying to give you more insight into the residual plot. I know when you go into R, you can easily get a residual plot. But what is the mathematics behind that? That's what I'm revealing to you now. A lot of secrets that you need to know about. Okay? Now, the variance of the error, of course, I think I've given that. Now, the other plot that I call the standardized residual is now going to be this guy. Look at that. That is the standardized, the residual that we'll talk about. Okay? It's going to be that. Okay, now, but you know what? These are the traditional way of dictating outlier. Okay? Professor Cook now trying to look at this and say, okay, you know what? We need to modify something is missing, and this is Cook distance formula. But where is the Cook distance formula coming from? Look at IR squared is actually squaring this guy here. Look at what we do. Modifying, right? Take a look at that. Okay? The Cook distance now. Okay? That is a formula. Okay? You know where this R is coming from. You know HII. That I showed you the other time, right? Okay. Now, this is a person. I don't know whether you have met him before. He's a professor emeritus from the School of Statistics, University of Minnesota. Is known anywhere in the world. Anywhere in the world where you talk about outlier, his method has proved to be the best. At least for now, because things are changing. Maybe one of you may come tomorrow and say, oh no, I got a new improved technique now. Okay? Now, that is his full name, Professor Dennis Cook. Okay, now, large Cook distance actually means the observation is more influential. And what is the threshold when the Cook distance is greater than 1? Okay, when you calculate D and it's greater than 1, okay, then you know it's going to be influential. Of course, I gave you a code in R on Monday, how you can actually have access to Cook distance. You don't need to go through that formula. That was the formula, the program in R, in Python, in SAS, in statistical software around the world. What I'm just trying to show you now, just like what happened behind the scene. A lot of mathematics going on behind the scene. Now, take a look at this. We have this an example of a scatter plot, and there's a particular point that is far away from others, right? Even though it's on straight line. And we decided to compute the Cook distance, and we got that. There's no problem. I told you, anytime police pull you over, don't be scared, cooperate with the police, okay? It is not everybody they pull over that will get tickets at the end of the day. Just like, oh, there's an outlier here, we're suspecting that, but this is not an influential one. We got a threshold. Take a look at this guy. There's a double tragedy here on this scatter plot. There is high leverage, there is outlier. Two tragedy. When we calculated that, oh my God, look at that, 4.7. That is far from, that is greater than 1. Okay? And because of that, we're basically going to say, there's an influential point. Okay, what are the strategies for dealing with influential observation? Number one, we simply remove. But when you remove? When you realize there's an error in recording. That is the only condition under which we're basically going to remove. Now, we need to identify the cause. Before we take an action with an outlier, we need to identify what causes that. When you are doing your research in your laboratory, and it could be as a result of faulty equipment or incompetent lab assistant, okay? Or a geologist searching for oil deposits. Imagine before United States become an energy, independent, when they were searching for oil deposit, they didn't get, and it get to a point they started getting. Of course, there's going to be stuff that we can call an outlier. Now, situation where we cannot discard just because it is not due to erroneous imputation, we basically need to fit a different model that I call robust statistical model. We got a lot of robust regression model around. Weighted least square is one of them. Okay, there are different kind of robust regression model around. What do I mean by robustness? Robustness is the ability of a model to be less sensitive to violation. That's what we mean by that. Okay, and of course that was what I work on in my PhD work. Okay, I'm actually going to stop here today, and on Friday, I'm going to continue from further regression diagnostics, R code. Is there any question before I go today? Now, before I go today, I have this announcement.